Hello everyone, welcome to the e-learning program of K.T.H.M. College Nasik. I am Dr. M.K.Deore from Department of Physics, K.T.H.M. College Nasik. Dear student, in this lecture we are going to see about the concept of reciprocal lattice. Now in this lecture we are going to discuss about the concept of reciprocal lattice, use of the reciprocal lattice, expression of the reciprocal lattice, and the relation between the direct lattice and the reciprocal lattice. Students, in the first lecture we have seen about the lattice points and the basis, and also the formation of the crystal structure. We have seen that the crystal structure is formed by associating with every lattice point by a unit assembly of atoms or the molecules in identical position. Now in this figure, see here, this is the two-dimensional area of the lattice point. Now if we consider the every lattice point acts as an atom, now then number of the atoms are arranged in the different planes and they are parallel with each other. So the every point gets surrounded with identical atoms, or the every atom is get surrounded with identical atoms, and its arrangement is periodic. So these are the number of the atoms which are in one plane, and that is known as the atomic plane. So in case of that, the every type of the crystalline material, there are the huge number of the set of parallel planes, and their orientations are different in different directions. So such a type of the arrangement is also known as the real lattice or the direct lattice. So with the help of real lattice or the direct lattice, we get only the information of the crystalline structure, but to describe the any crystalline structure we need the real lattice or the direct lattice. But to get the more information or the detailed informations about the any type of the crystal, such as the atomic arrangement in that crystal, the interplanar distance between the two planes, the lattice constants, etc. For that we need to study the X-ray diffraction of the any type of the crystals. Now the X-ray diffraction from the any crystalline material we will study in details about the Bragg's X-ray diffraction in next chapter. Now here, consider here, these are the all crystalline planes which are parallel with each other, and if the X-ray get incident on these atomic planes, now then the rays will be get diffracted. Now then Bragg observed that from this X-ray diffraction he plotted the graph of the intensity versus theta, and this X-ray diffractogram gives the information about the orientation of the plane and also the interplanar distance between the planes. From this X-ray diffractogram we can also determine the lattice constants. But in case of that the X-ray diffraction, Bragg's X-ray diffraction, there is no direct relation between the Bragg's peaks and the different planes. And in case of the Bragg's X-ray diffraction, it is difficult to visualize the set of the parallel planes in the crystal lattice because the orientation of the planes are in different directions So it is difficult to visualize such a set of the parallel planes in direct lattice, and such a difficulty solved by the German physicist P.P. Ewald in 1920, and he has given the concept of reciprocal lattice, which is used to visualize the set of parallel planes in a crystal lattice. Now that means the reciprocal lattice gives the representation of the set of parallel planes. So in this way, by using the Ewald construction, and the concept of the reciprocal lattice, it gives the representation of a set of the parallel planes. Therefore, the concept of the reciprocal lattice plays a very fundamental role in the study of the X-ray diffraction pattern produced by the crystal. And so, in case of nowadays, to study the different properties of the materials, we need to study the crystalline properties also, and for that we need to do the X-ray diffraction of such a type of a different types of the crystalline materials, and with the help of the reciprocal lattice we can determine all the we can obtain all the information related with the crystal structures of the different material. So the reciprocal lattice having the very important role in X-ray diffraction study. Now see here, this is the two-dimensional lattice, and here by using the translations, by using the primitive translations vector, we can obtain the square array. Now this picture shows that, now this is in case of that the crystal lattice. So if we take the reciprocal of this real lattice, now then the picture will be like this. Now these are the photographs of the real lattice and the reciprocal lattice. Now then see here, in case of that the real lattice, we are using the translation vector, and that gives the vector r is equal to n1 vector a1 plus n2 vector a2 plus n3 vector a3. But now in case of the reciprocal lattice, we are getting the reciprocal lattice vector is equal to be the h1 b1 plus h2 b2 plus l b3. So here the reciprocal lattice get expressed in terms of the HKL. Now then see here how we can represent the reciprocal lattice in case of that the three-dimensional arrangement. Now consider here this is the cube. Now then if we consider here the edge of the cube is equal to the 5 unit. Now then if we consider here, now these are the different planes. Suppose here, now this is the x-axis here, this is the y-axis here, this is the z-axis. Therefore now this plane having the coordinates 0, 0, 1. Okay, now this plane having the Miller indices, you can say that the Miller indices 0, 1, 0. Now this plane having the Miller indices 0, 0, 1. Now then if we consider the any arbitrary origin Now consider here that O dash is the any arbitrary origin, and from this origin if we draw the normal to this plane here. Okay, now then see here. Now this is the plane having the Miller indices 0, 1, 0. Okay, now then, and this is the plane parallel to this. These two planes are parallel with each other. Okay, now then if we consider here the distance between these two planes equal to be the 5 unit. Now then draw the normal from this arbitrary origin and terminate at the point where the distance will be 1/2 of the edge of this, or 1/2 of the distance between these two planes. Suppose if we consider here the distance between these two planes equal to the 5 unit. Now then the reciprocal of this will be equal to, that is 1/5 is equal to the 0.2 unit. Therefore, when you will draw the normal from this arbitrary origin and when it is passing through this plane, then terminate it at the point where you will get the reciprocal of the distance between these two planes, and that point is known as the reciprocal point. Now then in this case here, if we consider these two planes are parallel with each other, now then the same thing here, if we consider the upper plane and the lower planes are parallel with each other, again if we draw the normal from this arbitrary point and which is passing through this 0, 0, 1 plane, now then terminate at the point which is at a distance of the reciprocal of the distance between these two planes, and that acts as an reciprocal lattice points. Now in this way, in case of that, the any type of that crystal, now then what will happen here, if we consider this number of the planes, now then if we consider the another number of the planes, now then the same thing, you will get the different reciprocal lattice points, and these reciprocal lattice point represents the set of these two parallel planes. Now in this way, now these are now the corners of this cube are acts as a direct lattice, but now this point acts as a reciprocal lattice. So now in this case here, we can draw the number of reciprocal lattice in any type of the crystals, and that is a reciprocal lattice represent the set of parallel planes. Now then we are going to see about the construction of the reciprocal lattice. Now then see here, now in case of that, this is the two-dimensional square, two-dimensional lattice array, and in this case here, if we consider here A and B are the fundamental translations vectors, now then if there is the formation of the square array, so now in this figure we can see here, now then how to construct a reciprocal lattice in case of the any type of that the crystalline material or any type of the two-dimensional array or the three-dimensional array. Now then see here, in this case here, suppose if we consider here, now this is the x-axis, y-axis and the z-axis, and if we consider the any arbitrary origin, now if we consider here, this is one of the plane that known as the HKL plane, and this HKL plane which is at a distance DHKL from the origin O. Okay, now see here. Now then in this case here, the first point is to select the any arbitrary point in the direct lattice as a origin. Suppose here, now if you consider the point O is the origin in the direct lattice. Now from this common origin, draw the normal to each and every set of the parallel planes in the direct lattice. Now then, if we consider the origin is also in one of the plane, now then at some distance, if we consider this is the one of the plane, it is at a distance DHKL having the Miller indices HKL. Now then draw the normal from this from the arbitrary origin O. Now then fix the length of each normal equal to the reciprocal of the interplanar spacing of that set of the parallel planes HKL. That means now you have to terminate this normal at the point where you will get the distance reciprocal of the distance between the two planes here, and that point is known as the reciprocal lattice. So we get here the sigma HKL is equal to be the 1 divided by the DHKL, where this sigma is known as the reciprocal lattice vectors. So here, and this DHKL is nothing but the distance between the two planes here. Now then place the point at the end of the normal. So here this point where the normal get terminated, and that is known as the reciprocal lattice point. So it is very important how to construct the reciprocal lattice. Now in case of the any type of that the reciprocal lattice, in case of that the any type of the direct lattice. So here now this is the direct lattice. Now then here after constructing the reciprocal lattice, in this direct lattice we get the different points other than the direct lattice points. Now then see here, now we are going to obtain the expression for the reciprocal lattice vectors. Now consider here a plane representing by the line 1. Now see here, this is the two-dimensional square lattice, and in this two-dimensional square lattice, if we draw the any one plane here, now then this line acts as a plane, say as the line 1. Now then by the property, now then in these diagrams here, if we consider this is thus by using that the fundamental vectors A and fundamental vectors A and B, there is the formation of the square array. Now then if we draw the normal from point O on this line 1 and say as it will be terminated at the point B on this line 1. Therefore, the coordinate, the intercept of the x-axis, intercepts of the x and y axis are the A by K and the B by H. The distance between these two planes, you can say that this normal from the point O to the B equal to be say as the D. Now then from the geometry of this figure, we can observe the two triangles here, the AOC and the AOB. Now then by the property of the similarity of the triangles AOC and the AOB, now we can write here that the ratio of these two sides here, this, the OB divided by the OA is equal to the OC divided by the AC. Now then here, if we by taking the intercept corresponding to the x and y axis and by substituting this value, we get this relation here. Now then by solving this here, you will get the 1 upon D, it is equal to be the under root h square k square plus k square into the b square divided by the AB, and this is equal to the sigma. Therefore here that this sigma is nothing but it gives the magnitude of the reciprocal lattice vectors. Now then see here, now in this case here the same thing is here, that means here this is the previous figure here. If we take now then in case of that how we can write or how we can show the sigma in this figure. Now then, if we take the inverted image of this, now then you will look like this here. So here we get the sigma is equal to the 1 upon d. Now then, after taking the inversion of this figure, the figure will be like this here. So here you will get the intercept along the x and the y axis are the k by a and the h by b. Therefore, we get the expression for the reciprocal lattice is equal to be 1 divided by DHK. Now thus we can define the reciprocal lattice vector. The reciprocal space lattice is a set of the geometry points constructed in such a way that the direction of a vector from the one point to the another coincide with the direction of the normal to the real space, and the separation of those points is equal to the reciprocal of the real interplanar distance. That means, in shortly, you have to remember that the magnitude of the reciprocal lattice vector is nothing but the reciprocal of the interplanar distance. So remember this. Now see here, now in case of that, suppose if we consider here this is the direct lattice. Now that if we plot if we draw the reciprocal lattice of this direct lattice, now then it will look like this. The same thing is here. In case of that, this is the lattice points in the direct lattice. Now then you can see the reciprocal lattice of the direct lattice, it will be like this. So remember here how we can draw the reciprocal lattice in case of the any type of the direct lattice, in case of the any crystalline structure. Now then we are going to obtain the relation between the reciprocal lattice and the relation reciprocal lattice and the direct lattice. Now again we can define the reciprocal lattice. The reciprocal lattice is defined as the vector having the magnitude equal to the reciprocal of the interplanar spacing and the direction coinciding normal to the HKL plane. That means we can say that the direction of the reciprocal lattice vector is along the direction of the normal. So we can write here the magnitude of the sigma HKL is equal to the 1 upon the interplanar distance, that is the DHKL. Now then, for obtaining that the relations, you have to be consider the primitive unit cell of the crystal having the crystallographic axis, we say as the A, B and the C along the X, Y and the Z axis. Now then the volume of that the primitive unit cell is nothing but the area multiplied by the height. Now then we can write here the V is equal to the area of the base having the side. So here we can obtain the area of the base. Now this area of the base having the side B and the C multiplied by that height, the D10. So if we consider here this first the area of this primitive unit cell, and if we draw the normal to the plane 100, so its interplanar distance we can say that the T100. Therefore we can write here 1 upon D100 is equal to be that area divided by the volume. If we draw the unit vector n in the direction of the normal to the plane, now then this equation 1 becomes here. In terms of that the unit vector, we can write the sigma vector sigma HKL is equal to the 1 divided by the DHKL into the unit vector. Now then we can obtain the area of the base of the primitive unit cell, and the base of the primitive unit cell is nothing but the cross product of the vector B and the C. Now then from that the equation 2 we can substitute the value of the area there, and the equation 2 becomes here the 1 upon b 100 is equal to the area magnitude of the vector b cross c divided by the v. Therefore, we can write here the sigma 100 is equal to 1 upon d 100 into the unit vector is equal to the vector b cross vector c divided by the volume v into the unit vector. Now, but we know that now we can write the unit vectors in terms of these fundamental unit vectors, that is, it is nothing but the ratio of the vector b cross c divided by the magnitude of the vector b, magnitude of the vector b cross c. Therefore, now if we substitute the value of the unit vector here, now it becomes here the vector b cross c divided by the v into the vector b cross c divided by the magnitude of the vector b cross c. So we get here the sigma 100 is equal to vector b cross c divided by the vector. Therefore, the volume of the primitive unit cell and the volume of the primitive unit cell is equal to the v is equal to the vector a into the vector b cross vector c. Therefore, the above equation number 6 become by substituting the value of the v volume here. So we get vector b cross vector c divided by the vector a into the vector b cross c. Now the volume of the primitive unit cell you already studied in T.Y.B.Sc, that is nothing but the scalar triple product. And similarly, now in this case here, so we get here the vector which is normal to the plane 100, it gives the vector b cross vector c divided by the vector a cross vector b cross vector c. Similarly, we can obtain the relation for the another vectors here, the another vectors sigma 1, sigma 0, 1, 0 and the sigma 0, 0, 1. Now here, now in case of, now we are first draw the vector, draw the normal to the plane 1, to the plane 0, 1, 0, and so we can write the same, similarly we can write the expression for the vector sigma 0, 1, 0 is equal to vector c cross vector a divided by the vector a cross vector a dot vector b cross vector c. The same thing in case of that the sigma 0, 0, 1 plane. Now you have to draw the vector from this origin O normal to this plane here. Now this is the plane here, this is the 0, 0, 1. So here you have its expression becomes sigma 0, 0, 1 is equal to the vector a cross b divided by vector a dot in bracket vector b cross vector c. Now these vectors are considered as a reciprocal translations vectors. Now therefore we can represent now these vectors by vector a, vector b and the vector c. Therefore the vector a is equal to b vector sigma 100 is equal to the vector b cross vector c divided by the vector a in bracket vector b cross vector c. Similarly, vector b is equal to b vector sigma 0, 1, 0 is equal to vector c cross vector a divided by the vector a in bracket vector b cross vector c. Now similarly, in case of that, we can write here the vector c is equal to the vector sigma 0, 0, 1 is equal to the vector a cross vector b divided by the vector a dot in bracket vector b cross vector c. Now then we can observe here that vector a is, therefore here this is the a is nothing but that the vector sigma 1 vector which is normal to the plane 1, 0, 0. Therefore, the vector A is normal to the plane B, to the vectors B and C. Therefore, we can take the scalar product of this and it is equal to the 0. Now then, in case of that, the vector B is normal to, therefore here is normal to the vector C and vector A. That means vector C and the vector A. Therefore, we can take the scalar product and it is equal to the 0. So the vector B dot vector C is equal to the 0, vector B dot vector A is equal to the 0. Similarly, now here, now in this case here, this is the vector C is normal to the vector A and the B. So its scalar product is equal to the 0. That is this vector C dot vector A is equal to the 0 and vector C dot vector B is equal to the 0 we get here. Now then, we can write here the scalar product of the vector A, means reciprocal vector A, and the direct lattice vector A. Now then its scalar product it is equal to the 0. The same thing, if we take the scalar product of the reciprocal lattice vector and the direct lattice, now then by substituting these values here, now we get this expression here. Now then if we substitute these values, so it becomes here the vector B dot vector C cross vector A divided by the vector A dot vector B cross vector C. But we know that the property of a scalar triple product, we can change the position of the vectors in a cyclic orders. Therefore, this equation becomes, that is vector B dot the scalar product of the reciprocal lattice vector and the direct lattice. In case of that, the vector B, it is also equal to the 1. The same thing, now we can write in terms of that the reciprocal lattice vector C and the direct lattice vector C. Now its scalar product is also equal to the 1 here. Therefore, we observe that the vector A dot vector B. Now in this case here, these vectors are the orthogonal, while the vector A dot vector A, that is the scalar product of the reciprocal lattice vector and the direct lattice vectors, now then it is equal to the 1, and this is the reciprocal part. Therefore, with the help of the reciprocal lattice vectors A, B and the C, we can construct the direct lattice. We can construct the lattice. We can construct